Now we are discussing about variation of the pressure with the depth. This time we are considering a fluid at rest in a container, and we are discussing 2 points, the point 1 and point 2. Here the point 1 pressure is denoted as P1 and point 2 pressure at point 2 is denoted as P2. The fluid is in still condition, there is no motion, and whatever the element we have considered, this is a cylindrical element. The area of this element is A and height is H. So we have taken 2 points, one at the top end and the second at the bottom end. Now because this fluid is in rest, so the resulting forces means the force which is acting from the top and the force which is acting from the bottom, they should balance. So P2 minus P1A, that must be equal to mg. So here P2 minus P1 is equal to rho gh, because m is equal to rho into h. So that's how we have considered this equation. But this time we are taking the point 1 to the atmosphere, so above the container. So at this time, the point 1 pressure we are calling this as a PA, atmospheric pressure, and point 2 pressure we are calling as a P. Then P minus PA is equal to rho gh. So which is equal to P is equal to PA plus rho gh. So if we consider this pressure as a P, and when we go to the depth below the surface of the liquid, the pressure increases by rho gh. If the atmospheric pressure is PA, and if we are going down to the bottom of the liquid, then it will increase the pressure by rho gh. Similar thing happens in the ocean also. When we want to measure the pressure at a particular point at depth, example at 100 meters or 1 kilometer, we can say the atmospheric, it is the pressure of the atmospheric pressure plus rho into g into that 100 meters or 1 kilometer. That's how we calculate the pressure. This is called as gauge pressure. This extra, whatever this excess pressure we are taking, this rho gh, this is called as gauge pressure at that particular point. So gauge pressure means on this rho gh is the gauge pressure. So this gauge pressure, or whatever we are taking the pressure at a particular point in the fluid, that is not depending upon the area, that is only depending upon the height. So that's why whenever we want to calculate the pressure in the ocean, we never calculate what is the surface area, or we never see about the cross-sectional area. We only consider the depth, because the pressure depends upon this height h. So the liquid pressure is same at all points at the same horizontal level. This is called as hydrostatic paradox. So if we take 3 vessels, those 3 are different vessels, and this is the scenario. C and A and B, these all are different vessels, but these 3 are connected through a common pipe here. Now, because the same pressure is being exerted at the bottom of all these 3 vessels, if I remove liquid from vessel C, the vessel C height will come, example, it will come to the point 1. Then surprisingly, the vessel A height will decrease and vessel B height will decrease in such a way that they will bring back C to the new height to such that the heights of the water in A and B and C, they all will be in the same height. This happens to each vessel. When I remove water from vessel A, so if I call this position as a 1, then the vessel B water will decrease and vessel C water will decrease in order to make the vessel A's height to reach a particular point 2, such that all these three vessels water is in same height. This is hydrostatic paradox. With this simple example, we can explain what it means.